what does delocalization and aromaticity have in common? Well, let's have a look. We've said already, we know that this can be delocalized, okay? We've got a double bond, a double bond, a double bond. There's no single carbon bonds in between. So if you were to draw the p orbitals into these, you would see that they were all interconnected. So we're going to ask the question, but what if you put it into a ring structure? So if you took this and put it into here, you would get an aromatic system. So aromatic compounds are cyclic unsaturated molecules. So again, if we now look, remove the fact that we know that there are we've drawn it with fixed double bonds. Let's forget that for a minute. We have a ring of 6 carbon atoms. Now, without the p orbitals, without the ability to form double bonds to have pi electrons, this would be like a sugar. And we know that the sugars wouldn't be flat and planar, they would bend to accommodate the bond angles. But in this case, we have got, at the moment, an sp2 hybridized carbon. If you go back to Dr. Ullman's lectures, we've got this as sp2. So each of the carbon atoms has a p orbital which has 1 electron in it. And so because those p orbitals are all interconnected, there's no breaks in between them, they are next to one another, so one carbon next to another carbon, we can have this orbital overlap. And what that means is the electrons can be distributed, delocalized, between the entire ring system. Now, in reality, they're not all going to sit in one place. They are going to be distributed more evenly because electrons like to repel one another, so they will eventually end up as far away from one another as possible, but they can delocalize around that system. Okay. And we'll look in a minute at the kind of energy level bit that we're talking about. So all you need to remember is if you've got this kind of 3 double bonds within a ring system, it's going to be an aromatic system. When you move into part 2, you'll start to see examples where you might be able to put a nitrogen in there, for example, or an oxygen in there. And it can still be aromatic, but that's next year's material. But if you happen to see something with a nitrogen or an oxygen, then you might want to still think it could be aromatic. Okay, so why does all this matter? Well, by doing this delocalization, what we actually do is we are taking the unpaired electrons that are in those p orbitals and we are going to pair them up into molecular orbitals. So just like you were doing with Dr. Ullman when you were looking at sp2, sp3 hybridization, what we're doing is taking the p orbitals and effectively saying, well, let's combine those p orbitals into some kind of molecular orbital. Now, this is just for information. This isn't something which I would be expecting you to reproduce in an exam. It's just to give you an understanding, slightly deeper understanding of what's going on. Okay? So we have our energy levels, we have our atomic orbitals. So these are the p orbitals. Now, they are all, if you just left them, they would all be of equal energy, and they would all have just a single electron in them. Okay? But what happens is when we get them into this aromatic system, when we get them to the point where they can form these molecular orbitals, then what they do is that they start to pair up the electrons. And what that has the benefit of doing is by creating these molecular orbitals, it just changes the energy. It becomes more energetically more favourable. And that's the key term to take away. This system is energetically more favourable. So as a whole, the system is happier, the system is more stable. And that's because by pairing up, the energy of those orbitals drops slightly. So don't worry about the kind of anti-bonding molecular orbitals. The key thing is you pair it up into a molecular orbital, an aromatic molecular orbital, and it reduces the energy. And reducing the energy makes this more stable. So that's the key take home from this. Okay, so all you need to know, put it into a ring, it makes it more stable. And it's more stable because the bonding in there, the orbitals are at a lower energy. That's all you need to know. You don't need to reproduce this. So let's just think about what else is important. Well, in these aromatic systems, the carbon is sp2 hybridized. Okay, we can see that it's got 3 other groups attached to it. Okay, 2 of them are carbons. In what we're seeing so far in benzene, 1's a hydrogen, and it's got this unbonded p orbital, which we're now pairing up into this aromatic pi orbital. But if it's sp2 hybridized, that means it has to have a 120-degree bond angle. You know, we can see that here. Okay, look, we've got 120-degree bond angles. We've got something which is sp2 hybridized. It's flat and it's planar. So again, we draw it like this, and you can see that 120-degree bond angle. So at the moment, we're looking at a 6-membered ring. But can we look at things that are bigger than that? So we've got a 6-membered ring where you've got a double bond, single bond, double bond, single bond, double bond, single bond. You could do the same thing in an 8-membered ring. So cyclooctatetrene. Okay, double bond, single bond, double bond, single bond, double bond. Yep, you can see the pattern there. So the p orbitals in here are going to overlap. Okay, just like they could overlap in here. So can we look at this and say, is this aromatic as well? The answer is no. And the reason it's no is because cyclooctatetrene can't hold the carbons in a 120-degree bond angle and still be flat and planar. Okay? At the moment, it would have a 135-degree bond angle, which means it can't be flat and planar, so it's got to bend out of plane. And one thing that we know is that electrons really aren't good at going around corners. Okay? So for the electrons to be moving between these orbitals, between those p orbitals, they're not going to turn a corner. If they're all in the same plane, they're happy to do that. But if the electron has to change direction, it really doesn't like to do that. And in fact, the way, you know, that what we do is we use that ability that electrons don't like turning corners. We put them into big magnets and force them to turn corners. And what they do is they let off lots of electromagnetic radiation. And we then use that for various scientific experiments. But what we know is electrons don't like going around corners. So that means that this is not planar anymore, which means it can't be aromatic, because we are not getting that reduction in the energy level of the orbitals because we don't have this orbital overlap. That will come out in a little bit more detail in a minute. So there's another way, so we've got to remember that they've got to be flat and planar. Okay. The other thing we can start to do is there is actually a rule we can use to look at how many electrons there are in the system and whether that will make it aromatic or not. And that's called Huckel's rule. So Huckel's rule asks how many pi electrons do we want? Okay. And let's take what we know already. We know that benzene is aromatic and it has 6 pi electrons. And we know that cyclooctatetrene is not aromatic and it has 8 pi electrons. And we can use Huckel rules to actually determine and to tell us that that's correct, that benzene is aromatic and the 8-membered ring is not aromatic. This is where I always find people ask questions about this. So we'll try. So Huckel's rule says, and the key things here is it's a planar. Remember, we've talked about bond angles and whether it can be planar. A planar cyclic conjugated system. So conjugated is another way of saying delocalized. So I'm putting it in there because you will see that term used. Conjugated means you've got this single bond, double bond arrangement. So it needs to be a cyclic, conjugated or delocalized system, will be particularly stable, therefore aromatic, if the number of pi electrons equals 4n plus 2. And all that means is that n can be any whole number. It can't be a half number, it can't be a decimal point, it has to be a whole number. So that actually really limits the number of electrons it can be. So it can be 0, it can be 1, it can be 2, it can be 3, 4, 5, and so on. Okay? So it can't be 1.5. It can't be 2.75. So if you are trying to work out whether it's aromatic and you take your number of electrons you take 2 away from it because you have to plus 2, and then you divide it by 4, and it isn't a whole number, then it's not aromatic. Okay? So we'll have a look at 2 examples in a minute to test that. Okay? So all you have to remember is n is any whole number, and that's what you would have to work out to be whether something was aromatic or not, or whether it followed Huckel's rule. So if we take benzene, okay, so benzene has 6 pi electrons. So does that fit Huckel's rule? So if it has 6 pi electrons, and we're saying Huckel's rule is 4n plus 2, well, let's take 2 electrons away from our 6. We end up with 4 electrons. If we divide that by 4, we end up with 1. So where n equals 1, Huckel's rule says that there would be 6 pi electrons, and that would be aromatic. And that's what we get. So let's have a look at a couple of other examples just to test this. So do we think these are aromatic or not? We've got 10 annuline and we've got 14 annuline. Okay, so this one, 10 annuline, we've got 1, 2, 3, 4, 5 double bonds. In each of those double bonds, you're going to have 2 pi electrons, so we have 10 pi electrons in total. So if we look back at Huckel's rule, the 4n plus 2 should equal 10. So we take 2 of them away, we've got 8 pi electrons. We divide that by the 4, our n would be 2. So that suggests that that would be aromatic. So let's look at 14 annuline. We've got 1, 2, 3, 4, 5, 6, 7 double bonds. Therefore, we have 14 pi electrons. We've got 14 pi electrons. If we take our n plus 2, our 4n plus 2, we take the 2 away, we get 12. We divide that by 4, we get 3. So that, again, seems like it would fit Huckel's rules. 4n plus 2 to equal 14. If n equals 3, which is a whole number, it suggests that it would be aromatic. But only one of these is actually aromatic, and that's the 14 annuline. The 10 annuline, it's got the right number of pi electrons, but I always like to just throw in that little twist to the tail. Okay, so it's got 10 pi electrons, but it doesn't have 120-degree bond angles, does it? If you were to work this out, it actually has a 144-degree internal bond angle. Okay, if you take the 180-degree line, you'd get 36 on one, and the inside would be 144. So it's not 120. And what that means is to make it 120, you could redraw it. If we redraw it like this, which is the same thing, then it looks right, doesn't it? It looks like it should be a benzene ring. It looks like it should be aromatic. But the problem is, there's got to be 2 hydrogens here. And if you draw it like this, those hydrogens are going to hit into each other. So you can't draw 10 annuline in a format which allows it to have 120-degree bond angles and be flat and planar. But the 14 annuline, you can, because we've drawn it like this. It's got 120-degree bond angles. There's no clashing of the hydrogens. Everything's okay. What I will say is we're very, very unlikely to be seeing these kind of 8, 9, 10, 11, 12, 14-membered rings. Okay, it's just to, Huckel's rule is important to remember, but it's more about being able to understand what's going on there, rather than I'm not going to, trick you with this kind of 10 annuline problem. Okay, we're going to mainly focus on aromatic rings, but it's just to make you aware of what Huckel's rule actually means. We're going to be looking really at benzene. Okay, so with that in mind, we're going to go back to benzene and just do one last little bit of revision on it first. So, Kekulé structure. Okay, those of you that have done A-level will have come across Kekulé structure. Those that haven't, maybe not. But what we learn, which is still true today, is that this representation of a benzene ring is flawed, okay, because we're drawing these fixed double bonds. Okay, what we learn is that if this thing is, we've got this aromaticity, we know that those double bonds aren't fixed. So what often happens is that we draw our aromatic ring with this circle in the middle. And the circle represents the delocalized pi electrons. Okay? And we know that because we've just looked back at why that happens. We've looked at the energy levels. We understand that it is not fixed double bonds, that in reality, those pi electrons are in this orbital cloud above and below the sigma bonds. The problem is, using this representation when we're drawing curved arrow mechanisms, where we're talking about the movement of a pair of electrons, gets very complicated very fast, and you'll see why later, because what we'll learn is that not all of the atoms, the carbon atoms in benzene, are actually equal, especially when you start adding other substituents to it. So although we know that the Kekulé representation is flawed, that's the one we're going to use predominantly to talk about the mechanistic chemistry. And we're doing that because we know about this delocalization, and we're going to use something called resonance structures to explain that later. Okay? So what we're going to do is these curved arrows. So this double arrow indicates a resonance structure. What it's saying is, yes, we're drawing these double bonds in these fixed positions, but we know that lone pair of electrons could equally be there. This one could be there, this one could be there. And so the double bonds could be drawn completely differently. We could have also written it going the other way. Okay? But we're going to use that to represent our aromatic system. Okay? If you feel that you desperately still want to draw it like this, and you can make sense of it, okay, that's fine. We wouldn't be saying that was wrong. But what I'm saying is I will be drawing it using the Kekulé representation, and I'm using it for these specific reasons, because it helps show the movement of electrons and understanding why the positive charge, for example, on a benzene ring, which we'll see later on, why it can move around the ring. Okay, so the last thing, just as an aside, because you will see it in different drugs as you start looking around, is that aromaticisms can contain more than one ring. So you can have things like naphthalene, anthracene, quinoline. This is where I said we can start to introduce other atoms other than carbon there. We're not going to worry about that too much this year. That will come next year. But it's just to make you aware that if you see these kinds of systems, you can treat them as aromatic as well. Okay? It's just worth going back to, we had our 10-annuline before, and I said this isn't aromatic, but naphthalene is. Okay? And that is, the difference here is that, as I said, in annuline you had these two hydrogens that there's not space for them to actually fit flat and planar. They have to be twisted out of plane. Okay? But in naphthalene, that doesn't happen because you've got this single bond between these two carbons which replaces those two hydrogens. And so naphthalene can have this flat planar, and it's got 10 pi electrons. Anthracene is even larger, it's got 14 pi electrons. Okay. Don't spend too long worrying about this. It's purely just when you see these, be aware that they are still aromatic. All the stuff we're going to focus on that's really going to matter this year is going to be on single aromatic rings. Okay, so we've done a lot of, that's all been background, just to get us to this point that we understand what an aromatic ring is. Hopefully it's been a refresh and a recap for most of you. If you've never seen this stuff before, you need to spend a bit of time going away and make sure you really understand what an aromatic ring is.